technologies. So basically, let's see if I click. So what I wanted to do then, as I said, is talk a little bit about the original vectory model for Anopheles and malaria transmission, the generalization of the vector model so that we can model other types of vectors that have different relationships with rainfall in particular. And then, as I said, the machine learning. Sorry, is there a question there? I can hear. No? Okay. Okay. Maybe let me just say okay here. I don't know if maybe it's an idea to mute the lecture theatre microphone for a moment, unless there are questions, and then you could unmute to interrupt me at any time. Just because I hear quite a bit of background noise. That's okay. Can you hear me? Sorry, let me go back. Am I unmuted now? I should be, yeah? Okay, I think I'm unmuted. Can you hear me okay? I don't know why I became muted there. Yeah, okay, my audio's on, good. Okay, sorry, that was an inauspicious start. So basically, and some of the work that we're doing more locally in Europe as well about a monitoring system. And then just quickly mention at the end 2 new projects that we have starting in the summer. Okay. So a lot of you are familiar already with the key climate relationship and the key climate drivers of basically malaria transmission. But just to kind of remind ourselves, basically, you know, the temperature, as we know, has a myriad of influences on both the adult vector and also the immature stages of the larvae life cycle. So warmer temperatures speed up the development of the larvae. It also speeds up the gonotrophic cycle of the egg, basically development in the adult female. But high temperatures increase the mortality of both the adult and also of the larvae. Okay, so temperature has these 4 key impacts. The adult female, of course, if she basically through a blood meal acquires the infection of the parasite development inside the mosquito is also temperature sensitive. So basically, the warmer it is, the faster the parasite develops inside the mosquito. So for the parasite, it's really a race against time to develop and have the sporozoites ready to be injected in the salivary glands of the mosquito for a second and subsequent bites before the mosquito actually dies. So basically, if the mosquito dies before this second bite, of course, then the parasite is eradicated with the death of the mosquito. So the temperature impacts are quite numerous and diverse, but rainfall also, of course, has a strong influence when we're looking at the Anopheles species such as Anopheles gambiae, because it provides, of course, the temporary ponds in which the adult likes to lay her eggs for the larvae stage of the development cycle. But this relationship can be very nonlinear because, of course, more rain provides more breeding sites in general, but also extreme rainfall events, high intensity events can actually flush out smaller stage, early stage larvae from ponds and actually have a detrimental effect and actually clear out larvae. Okay. So just putting 2 of these relationships together, this is this classic paper by Craig, for example, that looks at the temperature effect on the length of time it takes for the parasite to develop. And so as it gets warmer, basically the parasite develops more quickly. So this duration of this development drops off very quickly. But at the same time, the daily survival rates in this also drop off as we get to higher temperatures. And so if you put these 2 effects together, this is just 2 of the 5, of course, you get this curve, which essentially says you have this sweet spot in terms of the parasite, where it has its highest probability of basically surviving long enough the adult mosquito to pass it on at temperatures around 28 to 32, 34. Now, one thing we should emphasize with all of these is some of these relationships have a very high level of uncertainty. So some of these are studied, these relationships in labs, in controlled environments, and basically things such as the survival rate can vary greatly, both between experiments and then also how these experiments translate into a field environment where there are lots of microclimates and niches and so on and so forth. Means that in fact it's not so clear cut. There's a great degree of uncertainty. Mortality curves, for example, can vary drastically between various schemes and implementations. So just these relationships, even though they're studied in detail, can basically have a high basically impact, a high level of uncertainty. Okay. I just heard recording and stopped the message. Okay. And the other kind of classic paper, this is again a paper by Pomblies showing how this is the week of the year, how this is the rainfall trace in Niger, and then we have this delayed seasonal transmission of the malaria, which is delayed by 1 to 2 months, which is a temperature-dependent delay, of course, depending on these cycles spin-ups. But you can see how the provision of the breeding sites basically determines the mosquito season in Africa. So this is actually quite different when we'll see later when we come to Europe, of course, in the mid-latitudes, where our cycles in terms of the seasonal cycle are much more driven by temperature rather than precipitation. Much more driven by temperature rather than rainfall. Okay. So I wanted to kind of give an introduction to the vectory model. I know some of people maybe have already used it or seen it or so on, but I wanted to give a little bit of background. Okay. So the motivation originally for developing this, my background is actually in the climate sciences and dynamics in the tropics, clouds, convection, and so on. But I was involved in a project, a European project, which started actually now 15 years ago, which was looking at climate health impacts. And so I wanted to understand a little bit more about the dynamical model in that project. And it seemed that there were quite a few factors there which weren't accounted for in that model. And so that kind of motivated me to, on the side, as a side project, try and develop a new model. And these were the kind of goals I had in mind at the time. It needed, similar to the Liverpool model, it needed to account for the temperature relations on vector larvae and parasite life cycles. Okay, so using the relationships wherever possible measured in labs. It needed to account for the nonlinear link to rainfall, including flushing and the geometry of temporary ponds. So that was one area where the hydrology was really not treated very well in the Liverpool model. It was just a simple linear relationship with no delay. I really wanted to try and actually have the should we say, the integrated hydrology of ponds represented in the model. It needed to also have a link with the population. So basically, it needed to be a gridded model, much like the Liverpool model, that can be run for a single location or a whole regional continent. And because it was running for a whole regional continent, it needed to be a model that focused on speed and simplicity, and also expandability. I'll mention this a little bit again later, some of the things we're trying to do to improve the way we represent the human components. And we're actually looking to have the possibility of actually linking it to an agent-based model for human mobility so that we can have a much better representation of how humans moving around can bring basically parasites from high to low transmission regions. Okay. However, the model was never intended to be a kind of a GUI point and click with a kind of a Windows interface and so on. So it is a model that was designed from the outset to have a little bit of investment in terms of learning how to run it and so on in a research and also, if possible, an operational environment. So there is a little bit of buying effort. Okay. So this human component and the hydrology were two of the areas where we really wanted to make a move on from the Liverpool model. But I have to say that also one of the big motivations in the first place was that it was not possible for me to play with the Liverpool model because it wasn't an open source code. Okay. So right from the outset, the key motivation was actually to develop a free and open source model for the community that's available in the cloud. You can go to GitLab and you can just basically clone the model right now after the lecture if you're interested. Okay. So the basic vector model, it's a dynamical model. And each grid location, if you're, for example, running it for a region, or let's imagine you want to run it for all of Nigeria, you could set up an array of grid boxes that cover Nigeria. And in each of those grid boxes, there are a set of equations that basically monitor the proportion and density, basically, of the larvae stages, so the eggs, and then we have the L1, L2, Li, Ln, I. So basically, the larvae stages are split up into a series of boxes, so we can represent the time delay accurately from egg hatching right through to adult emergence. And then it also has an equation for the female that basically represents the gonotrophic egg development cycle. Here we don't divide it up because this cycle is actually quite fast. And so with a daily time step, it's not that well resolved. So we haven't actually got an explicit representation anymore of the gonotrophic cycle in the model. Okay. So basically, you can imagine that the model essentially has these underlying equations where we have a rate of change of the larvae development, and then we have basically the oviposition, which is a function of T, of course, because the warmer the temperature, the greater this rate is. Okay, it's related to the vector density. And then we have a survival scheme, which is both a function of temperature and precipitation, because precipitation in high intensity events can lead to flushing and therefore mortality in the larvae. And there's also a carrying capacity term, which essentially is also where rainfall comes in, because we'll see in the moment that rainfall drives a puddle model, and that basically determines, in an integrated way, integrates rainfall, the carrying capacity term. Okay. And so this is where this equation is actually quite nonlinear, because of course then it's also related to the larvae. And then we have a larvae development rate here, which is a function of temperature. So you can see how temperature comes into this equation, both in the basically the gonotrophic cycle, the mortality, and then also the larvae development. And then we have the adult vector, basically has a rate of change, which is, and I've got a mistake here, this should be a lowercase t, sorry, for time, which is basically we've got the mortality here, okay, and then we've got the emergence term here, okay, which is here we have the emergence, which becomes a source for the adults. And then we have this D, which is diffusional movement. So the movement of mosquitoes from one grid cell to another is very simply treated at the moment with just a simple diffusion. It's not weighted. Wind doesn't play a role for this at the moment. There's no kind of upstream chasing of CO2 sources to find blood mills and so on. At the moment, it's extremely simple, but that, we could look at improving that in the future. Okay. So these kind of equations are familiar. Sometimes people that run SEIR models kind of bolt on a similar representation for some of the vector and egg, but not always. Sometimes they have a more simple representation. So by doing it like this, we're able to kind of build in these temperature dependencies and also the precipitation here through the carrying capacity and the flushing term explicitly from lab studies. And then on top of this, we have a classical just SEIR model for the host infection state. So basically, there's a memory for the vector sporogonic cycle as well as the gonotrophic cycle, where the mosquitoes, if they acquire an infection, they go through basically a development until they become infective to other humans. And again, this is temperature dependent. And meanwhile, the host, of course, if it picks up the disease, the parasite, there's also a development rate here, which of course is independent of climate because we're warm-blooded. But there is a simple representation of immunity inside this from Laneri et al., in fact, from the 2010 paper. Okay, I won't go into detail there, but just to say we have a simple representation of host immunity. Okay. So I'm going to just show a couple of examples of this model in use. And so one of the first things we tried to apply it to was seasonal forecasting, both potentially and then also in applications. Now, unlike forecasts for the atmosphere, where since the 1950s, of course, after the post-Second World War expansion of, should we say, the use of like telecommunications and so on, there was a big effort to basically connect up all of the world's Met services observations through the GTS, the Global Telecommunications Network, so the Global Telecommunications System, I think it stands for, where observations were collected in real time, near real time, in order to initialize forecasts. Now, of course, in 2025, we still don't have a system like that in any kind of health applications. The whole idea of early warning of health is quite a new phenomenon, even now, rather than reacting to outbreaks, to actually, maybe use climate information to try and preempt possible health problems in areas where maybe year-to-year transmission might be very high because you're in kind of fringe transmission areas. And so what it means is that due to the lack of information we had at the time, we actually instead had a kind of pseudo-analysis of the initial conditions for the should we say, the vector. So things like mosquito densities and their status in terms of their circumsporozoite rates was basically just achieved by driving the vectoring model through climate observations or analysis. Okay, so there was no real-time information about either the entomological state or the epidemiological state actually fed into this system at the time. So it was a rather idealized way of initializing these forecasts. So these provided the initial conditions for vectory, which was then driven by a climate forecast calibrated to remove spin-up and biases to provide a hazard forecast. So this was one of the early applications. The model was developed around 2012, 2013, and this was published in 2015. Okay, so give an example from that paper of what we were looking in terms of potential lead time. This is a little bit tricky to maybe see because these maps are quite small, but in each of these, this goes from January through to June, and then we have another set of maps in the paper from July until December. But just to give you an idea, what we're looking at here is we're looking at kind of fringe, should we say, transmission areas, okay? Now, of course, I'm choosing the wrong maps here, time of the year for, should we say, malaria transmission. It's only really kind of July, August, and September. But if you look in some of the southern areas here, what you see is you have basically the yellow is predictability of temperature and also of malaria. Green is malaria, red is temperature, blue is rainfall, and then white is all three. So if we focus on these southern eastern fringe transmission areas, we've got quite a lot of white dots at month 1 lead time, okay? And then when we actually go through to month 2, then a lot of these points basically then turn green, okay? And that means that we have malaria predictability, but we don't have temperature or rainfall predictability, or we have some yellows, which basically says we've got temperature and malaria. And then eventually the points you can see in the long term basically turn black. And so what that's saying is in the first month, we've got some kind of predictability in the atmospheric variables, but really it's lost by the end of month 1. Okay, there was no skill really in this system between, above maybe a month 2 for temperature. But that translates into early warning predictability out to month 2 or 3 in malaria just because of the delay. Even if you don't have forecasts and you just drive from analysis, you can get predictability in malaria out to a month or so just because of the delay between the rains and then on the onset of the transmission season. Okay, so that paper there was basically looking at this potential predictability. And then in a paper that came out a couple of years after that, we were looking at basically using the model in that project in Uganda. So we both compared to district health data and then also 6 sentinel sites. I won't show the results from the district data. We found that there was some skill in some districts. Often you'd maybe have skill in one district, but then the neighboring district, there would be 0 skill. And you found that the correlation between districts in the malaria cases was also extremely low. So sometimes they tracked the climate very closely, and then maybe in a neighboring district, there was no relationship at all. And the fact that the climate itself has, a larger scale normally to the anomalies would kind of indicate that the lack of agreement between the malaria traces themselves means that maybe in other districts, malaria variability might have been less climate driven. So we actually used the spatial correlation between districts to try and give a measure of how much of the actual explained variability was due to basically climate and how much was for other reasons or even data uncertainties. I'll just show you now an example of the early warning for like one location. This was Kanungo in Uganda. This was published in GeoHealth, and you know the results are not amazing, but at least you can see that the red line is basically normalized confirmed cases from this Sentinel site, and then the black line and the shading are like an ensemble forecast from this dynamical system driven by basically observed climate. And you can see, like, for example, in 2008, there's quite a bit of disparity, but we were pleased at least that we could get the evolution of, should we say, year-to-year variability, at least in a gross sense of like we were able to discern the high to low years. Unfortunately, we only had basically 6 years of data. These used to be published actually on a public website, but I made the gross error of actually presenting these at a meeting, and somebody from the American university that was collaborating with Uganda was at the meeting and asked me where I got the data from. And when they said, well, they're actually publicly available on the website, the website was taken down 2 days later, unfortunately. So there we go. I should have perhaps kept a bit quieter about that. So it's a pity because it would be nice to test the model on a lot more different environments, but trying to find, should we say, good confirmed data is always difficult. So if there are people in the room that are interested in collaborating to evaluate the model, for example, in Nigeria, I would be more than happy and open to follow that up and basically confront the model with as many different circumstances as possible. The model has also been applied to climate change problems. There have been model intercomparison studies, but I thought instead of showing those, I'd perhaps show an example where it was actually put into a context where it was intercompared with a number of statistical models. So this was a paper that was published in 2020 by Miria and colleagues, including myself, where she actually calibrated the model for Anopheles sakharovi in Greece, which is the traditional malaria vector that used to be responsible for malaria transmission until the disease there was eradicated. And now the Greek health authorities are very worried about the reintroduction there. And so basically the model was put in a mixed bag of other statistical, should we say, modeling techniques such as maximum entropy, generalized linear models, GLAM models, and also some kind of machine learning type models, and used against presence and absence data. Okay, and so here we have the malaria model, which was just using parameterizations for this vector taken from lab data were available. So there was no calibration here. And so basically the agreement actually with the niche models, which were trained on presence and absence data, was actually pretty good, considering there was no calibration involved in this at all. It was just a straight out of the box simulation. Okay. And so we have, for example, also good agreement with, for example, locations where there were traditional malaria or even secondary cases in one or two cases through importation here and these kind of contours. And so this basically was then used to kind of look at how over time the vector might expand its territory. And so we have an intermediate and a very high order scenario here. And we were looking at like through the 2040s, 60s and 80s, where both the niche models and the machine learning models and also Vectri gave a good level of agreement of how the potential territory would expand where the vector moved to higher elevations. Okay. So now I want to change gears a little bit and just talk about some of the more recent work we've been doing of extending the vector to the model to other vectors. Okay. And so first of all, there was a big, strong motivation to try and apply the model to Aedes albopictus. That's a tiger mosquito, which is an invasive species that arrived here from Asia in the 1990s. And in fact, Trieste, where I'm living in the northeast of Italy, was one of the first areas to actually have the vector. But it's really expanded in terms of its overall territory, but also its dominance within the territories where it was first introduced. I arrived in Italy in the year 2007. So that's nearly 18 years ago. And when I first arrived, it was extremely rare to see a tiger mosquito. I remember if I slapped a mosquito and I found it was a tiger, I would like excitedly show other colleagues and say, look, 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 there was a tiger. No, because it was still quite rare at the time. In the meantime, it's completely displaced the Culex species and that were predominant here before, and they're much rarer to find now. And nearly all of the bites that we have in the summer are basically the tiger mosquito is responsible. So anyway, there's a big effort now to try and ramp up observations of this nuisance vector, particularly because now we're starting to have locally transmitted cases of diseases such as dengue in the country. Trieste actually had lockdowns last summer where they went out spraying and to try and eradicate because we had secondary cases of dengue. So there's a real health concern now about this importation of this disease. So there are lots of egg trap data. This is a summary of these made by my colleague Miguel, who's just started a postdoc here now. He was visiting last year, working on this new project. And this was just published last year, where we were looking at the egg trap data. And you can see this is the 2-week average temperature. And this is the eggs in the egg trap data. And you can see this kind of threshold of around 10 degrees where eggs start to be present in these traps. And then there's gracefully an increase until we reach this kind of sweet spot temperature of a mean temperature of around 25, 26. And then there's a hint in the data that we're starting to get to that peak and there's a bit of a drop off. So the really kind of peak high values are found around 25. So, and then it starts to drop off a little bit. Okay. So one of the things when we wanted to turn the model to applying it to the tiger mosquito that we ran into trouble straight away was the representation of hydrology in the model. Okay. So the model has basically a pond model where rainfall is collected. It has a kind of simple mathematical representation of kind of catchment areas. So some of the rainfall is just assumed to drain off into the larger scale river networks, whereas some of it then is collected into small local scale ponds, okay, which can lose water through overflow or infiltration and also through evaporation, okay. Now this model was tested against observations in places like, this is actually in Ghana. I had a PhD student who was in a sandwich program. He spent part of his year in Ghana and he was using Ghana in the rainy season and he was measuring ponds. So these red lines here are rainfall. This is time of the year. And these are just different breeding sites on campus in KMUST. So you can see the evolution of the ponds and then our very simple pond model in the blue line, okay. So even though it was an extremely simple single equation, it did a good job of being able to represent the evolution of these ponds. And the same, we also tried it against basically an explicit simulation for a village in Niger, a 10-meter resolution. So this hydromats with the red line is an explicit solution, a 10-meter resolution of a mapped village of 3 by 3 kilometers. And these are two different versions of the vectory scheme. And you can see again, it has a good, these are two different rainy seasons. It can discern the differences between the rainy seasons. And the scheme can also represent the sub-seasonal variation in the pond availability. So it's not perfect compared to this explicit model, but this is an extremely complicated slow model with like hundreds by hundreds of grid points. And the blue lines here are just a single equation. Okay. However, we found that when we went to apply the model to Aedes albopictus, it really had a problem in the summer because, of course, in the summer in Italy, it's very dry and the pond availability would just basically disappear and the population would collapse. So the model has been updated recently to include two other water body classes. One is the breeding sites that might be found around the borders of permanent water features. So these large water features such as rivers and lakes don't provide breeding sites themselves because they have ripples, they have predators and so on. But in natural lakes, for example, you can have ponding around the edge, also rivers, which, for example, is very important for the Fenestus parameterization. And then we've also got a very simple parameterization we've introduced, which basically just links availability of breeding site with no rainfall link at all, in fact, to basically urban population density. And this is supposed to represent kind of man-made breeding sites, which are utilized by Aedes albopictus, Aedes aegypti, but also, of course, is important for Stephancy. So Anopheles stephancy is another urban breeder that's adapted to urban environments and can quite happily use these kind of containers and so on. So in urban environments, there's a mix really between the hydrology scheme, which is rain-driven, which represents rainfield sites in urban environments in that case, and also this scheme here, which represents basically, water storage containers and so on. Okay. So updating the hydrology, then we were able to actually simulate, this is for Bologna, the Aedes albopictus evolution, the temperature relationships taken from the lab. We're able to basically define very well the seasonal length, the onset, and also the cessation. And there's even a hint in Bologna that we managed to get some of the year-to-year variability correct. Okay, yeah. So that's good. And we use the model then to basically, driven by climate data, to look at the overall distribution of vectors predicted by the model today, comparing it to presence absence data here on the bottom left. It did a reasonable job of getting the kind of hotspots of where we expect a higher number of basically vectors, although there's a little bit of hand waviness sometimes with this because, of course, the vector hasn't yet diffused out to kind of fulfill all of its potential niche populations. As I said, it's still a vector that's in a transitional period of expansion in terms of its territory. So it's not found everywhere where necessarily the climate might be suitable for that vector to be present. Okay. So we looked at how heat waves basically affect populations of these vectors in Italy. So this is going from the 80s through to the 2010s. And so with like a gradual warming of the climate, heat waves basically have an impact of increasing vector populations over time in the model. Okay, because as we said, the temperatures in Italy are really kind of at or below the sweet spot. So generally, heating is basically, or high heat anomalies are beneficial to the vector. Okay, assuming, of course, as we said, that this linkage to rainfall is weak with this particular vector species. So we looked at, for example, as I said, heat waves by basically just clipping the temperature back to the 90th percentile of the June, July, August temperatures over the kind of the 30-year period. And in most cases, if we looked at heat waves, basically minus no heat waves, so that's the orange line and the green line, the difference is at the bottom here, heat waves were generally beneficial to the vector. But there were some cases where we got this kind of S wave in the vector population density. And so these were quite interesting. So we drilled down in the paper to have a look at these in more detail, where we actually had that the heat wave would first have a kind of a knockdown effect, and then there would be a bounce back and an overshoot. Okay, and these were generally in much hotter areas where the heat wave would expect it to be having a detrimental effect because then it starts to really impact the mosquito mortality. Okay, but we found that we had this rebound. So what was going on there? So we investigated that a little bit more, and it turned out that it seems to be that the lack of cannibalism in the model, and that's whereby when resources are scarce, remember these water bodies are basically resource limited, we had that carrying capacity. And so what happens is in the model, when we first have the heat wave, it basically knocks back, should we say, larvae through the enhanced mortality. But that means that then the remaining larvae are less resource limited. And so the emergence rate actually then bounces back and overshoots. So then we have a higher emergence rate. Okay. And I think the indication there is that we severely lack cannibalism in the model, because what happens is, of course, in cannibalism, the late stage larvae, when resources are scarce, actually feed on the early stage larvae. And so that enhances their possibilities of surviving at the expense of the lower. And it kind of basically makes the pyramid, the population pyramid, more straight. Okay, so one of the things now that we're doing is trying to represent the cannibalism inside the model to improve this and not get this bounce back. So I'm noticing the time. I'm about at the half an hour mark. I'm probably, if it's okay, I wanted to speak for another 10 minutes on the machine learning. I don't know. Am I okay if I speak for another 10 minutes? I don't know. Or do you want me to stop there? Just talking about the machine learning for interventions. Am I okay for time? Is there somebody in the room that can? Yeah? Okay, I don't hear any objections. So, okay, I'll just carry on for another 5 minutes then, and then I'll try and wrap up to leave time for questions. Okay. So basically, the model already has a little bit of a hybrid approach in terms of its calibration. So there are all sorts of different ways you can address calibration of these kinds of models. You can use Bayesian techniques. We actually implemented a particle filter technique. So it's kind of a genetic algorithm, so GA genetic algorithm, whereby it's a very simplistic approach where if we want to calibrate any model parameters, what we do is set up this large ensemble. So we actually would run M instances of the model. So this might be an ensemble size of 60, 80, or 100 models. Each model will have its own set of parameter settings. So these P's are the parameters that maybe guide the gonotrophic cycle length, the sporogonic cycle length, the relationships that link the mosquito to the hydrology, parameters that are associated with the mortality rate. Because if you remember at the beginning, I said we know these from labs, but there's a large amount of uncertainty, both in terms of the interpretation of the lab studies, but also how you translate that into the field. To give an example, temperature information, maybe it's from a gridded analysis or from a station. Well, over a grid box of, say, 20 kilometers, if you've got complex terrain, the altitude can change quite a bit, the land cover can change quite a bit, and that will all have an impact on the local temperatures which are actually experienced by the vector. And so there's an uncertainty even in, for example, the spatial variability of temperature. So all of these parameters can be tweaked, okay, around the default values. And so you would run, each of these models would have a slightly different parameter setting. And then the calibration simply says, okay, each of these has a simulation which you can compare to observations of cases or vector density or whatever it is. And you have a metric of the skill. So some of the models may be very good, and some of them less so, and some of them might be very poor at simulating the observed data. You then have a second generation of models, and the parameters are taken from this parent generation with a probability associated with that goodness of fit. So the better models have a better chance of passing on their parameters, which are then also mixed up. So you can have two or more parents. And also, as these parameters are passed down, there's a possibility of mutation, okay, where there's a perturbation applied in order to allow you to explore the parameter space, okay. It's in our case, if you want, you can keep the best one or even n models inside this ensemble, so you don't throw away your best model, okay. And eventually, over time, you expect that the model will converge towards a minimum where you'll have a set of very good models with a parameter setting, and then you can take the best or the best n models, okay? So there's a little bit of a constraint on this, of course. So just like with a Bayesian approach, where you don't want to just completely explore all parameter settings to have a very good fit to the data, but at the expense of having a very, very silly value set for one of the parameters, which is just completely outside of anything that you've measured in a lab by a long way. And so what we actually do is the cost function is actually a combination of both the skill of the model actually fitting the data, but also the departure of the parameters around what we think the default value is, okay? So will there be some kind of prior? And so the fitness basically is kind of minimized at a point where both the skill is at a maximum, but also the departure is at a minimum to give you the most likely model. So it's kind of a constrained search rather than just a free parameter search. Okay. So with Madeline Thompson, who's now at the Wellcome Trust, we basically had a look at doing this where we allowed, for example, model parameters to calibrate, or where we allowed climate parameters to calibrate. And this is a simulation for malaria transmission in the tea plantation area of Kenya near the Lake Victoria. The default model settings actually for this location, because the temperature was kind of close to the threshold of 18 degrees, we wasn't simulating any transmission at all. There was zero malaria. And so you can see that by allowing the model in the black here to calibrate its parameters, it could get a bit, some transmission, but it couldn't get that close because of the constraint on the parameters. But when we allowed for climate variability, then we could get a better simulation. It's not perfect, but we could get, for example, some of these like outbreak periods associated with ENSO, even if sometimes they were under predicted, okay, for CARICOM. So what I want to talk about now is the application of this calibration to actually deriving optimal intervention strategies. So we had a project recently that was funded by the IAEA, and they're interested in the sterile insect technique as a mode of intervention. This essentially entails the release. This essentially entails the release of sterile males, which have been treated by radiation. And those males, if the females breed with them, their eggs will be non-viable. Okay. Um, and so this is, reasonably, it's been around for a couple of decades, but it's kind of spinning up more. Quite a few countries have got trials in place to try and assess this. But if you look at the literature and you look at the trials, they have extremely large variations in how often they go to the field to release the mosquitoes, how many mosquitoes they actually release in the campaign, and so on. And so there's really a lot of uncertainty about optimal strategies for intervention. Okay, so what we did is we put a parameterization into the model for this. So we have a new prognostic equation for the sterile males. So this is MS. So we have a number of releases. They can have a different mortality because the treatment can mean that they actually have a shorter lifespan. Okay, and again, they can diffuse. And then we actually have a female equation because, of course, the females are not released. When they sterilize them, they don't release females because, of course, females bite and they can transmit disease. But we have to have an extra prognostic equation for females in the model who have actually then mated with a sterile male. So they have non-viable egg populations. And so this is related to the emergence rate, the proportion of the vectors. In this equation, you can also build in a competitiveness. I haven't got it in the equation, but there's a parameter actually I should have added here. You can call it a lambda, which determines if these males are equally attractive to the females and can basically mate at the same rate as wild males here. And then, of course, they have the normal mortality rate. This is the same as the standard female mortality. And so we set up the model to have like basically a release strategy, which is defined by 4 parameters. So each year, each season, we have to define the start date of the intervention, okay, the total number of treated males, the length of the intervention, and the number of releases. So for a given number of males, you could have maybe just 2 releases where you release a lot of mosquitoes, or you can have many releases where this is divided up into a smaller batch, okay? And of course, there's an economic cost. So this is actually in the model, there's a cost for actually the production of the males. And then there's also a cost associated with the releases, because often where these things are produced, because of course you need a radiation source and so on, this lab might be actually a long way from where the field study is. So for example, there's a campaign in South Africa to test this, and the place where these mosquitoes are produced is actually 500 kilometers from the release site. So in that project, the bulk of the cost is actually in the releases due to the necessity of going to the field, staying in a hotel and so on while they have the releases. So if you go once a week or once every 10 days, it has a big implication for the cost of the intervention. Okay. So just quickly now to show you the kind of the intervention. Here we have a log scale on the x-axis here, which is just the total number of males released in the season, and it's a log scale. So this is just one mosquito, which of course is ridiculous. You wouldn't just release one mosquito, but I just want to kind of go from essentially no intervention here up to more than 1 million. So most of the recommended or the campaigns are in this kind of range of between 10,000 and 1 million vectors. And as I said, these campaigns have a very wide dispersion in terms of the releases and the number of produced mosquitoes. Okay, so normally the intervention lies in this kind of area here. Okay, and then what we see on the y-axis is just the reduction in the mosquito density. So we go from having no impact at all, 0, to we get this kind of shaped curve where as we get out to 1 million mosquitoes, essentially we can have complete knockdown of the population. The different colored lines are the number of releases. Okay, so we only have 1 release here. This is 2 releases, 3. Okay, and then it starts to saturate as you go up to like 10 releases or more. Basically 20 releases here is the purple line, which is a release every 4.5 days. Okay. Now, if we look at, for example, the simulation, again, where we have a different start day in the year for this location. I forgot to mention this is for a location in West Africa. Okay, so we have basically the initial period at like 100 days, 130 days, 160 days. And as we go later in the year, you can see that the impact of the campaign gets less and less until we actually have a rebound here. So late in the campaign, we can actually have an enhancement in the mosquitoes through this. And again, I think this is again highlights the lack of cannibalism where you get this bounce back. Okay, so if you have a very late release after the main rains, it actually can have the opposite effect in this model. Okay. So what we did is we took in this model, a very idealized model, and if you notice, I haven't shown you any evaluations of the model against real SIT campaigns. This has been sitting on my desk actually for over a year. I'm really embarrassed, but we need to add that before we can go to publish it. So this is still work in progress that I'm going to try and finish up this spring. But what we have for this location is the blue line here represents guidance from the IAEA. So they have a guidance where they say, you should go into the field, roughly once a week. This is the kind of number of mosquitoes. You should start the campaign a couple of weeks before the rainy season. And so the blue line is basically a model, should we say, run using the guidance intervention. And instead, the orange stars here are saying, well, given a number of mosquitoes that you can release, okay, what would be the intervention strategy that would give you the most impact, okay? And so you notice, of course, that if we have very few releases, we can't have an impact with the change in the strategy because there's just no intervention is possible. And of course, when we have saturation, again, there's no impact possible. But in this intermediate zone, we have about a factor of 3 improvement, okay? So this is not on the economic cost. We could also minimize on that, but essentially this is just for maximum knockdown. If we change our strategy of just the release spacing and also the release timing, we can actually have the same impact for 3 times less in vectors, which reduces the cost of intervention, or we can we can have, for the same number of vectors, we can cover 3 times as much, should we say, site releases of areas and so on. So this is quite exciting. It shows that this very simple machine learning approach has the potential to improve guidance on SIT interventions. But as I said, we do need to evaluate the parameterization in more rigorously before we can go ahead. So basically, that was kind of all I wanted to say. I've probably gone over a bit, so I'm going to just quickly summarize in 1 or 2 seconds that we have this open source model now that accounts for the climate. It can run on a gridded area, as you can see. It accounts for population density. It's got parameterizations in it now for bed nets and SIT, okay, so far. And it's really, like I said, it's open source. It would be really nice. The more people are interested in evaluating it in anger, in different environments, the better. We've done this pilot study to show the potential use for simple machine learning to kind of help guide intervention planning, perhaps in a more cost-effective way. Okay, but again, this work needs to have more, should we say, confrontation with real data in order to have confidence in what we're doing here. Okay. And there are other areas of the model that we're looking at, actually, like as I mentioned, improving, so linking it with an agent-based population model. Okay. Just super briefly, we've got 2 new projects starting this year. So one will start, this starts in September, Climatize. So it's a project that ICDP is actually leading. It runs for 3 years, $3.5 million euros, 8 partners. It runs in 3 African countries. So it's in Senegal, Kenya, and Ethiopia. And it's basically trying to tease apart interventions from climate, so to better advise people. So if you're rolling out interventions in an area and malaria transmission goes down, it's to try and say, well, part of that reduction was actually the climate perturbations of this year, or vice versa, that climate's been working against you and your intervention was actually more efficient. Okay, so it's trying to help assess basically the impact of interventions. And then we're in another project as well, which is Convince, which is being led by Swiss TPH. It's funded by Unit Aid. And that's also, in a way related, it's to use climate-aware dynamical models and machine learning to learn how to integrate best new intervention techniques such as spatial repellents and sugar bait traps in the most cost-effective way. So there are 2 new projects. This is a 5-year project. It has a lot of field studies, and we have a modeling role there. So I think I'm going to stop there, actually. I've got a few extra kind of supplementary slides, but I thought I'd leave time for questions. Thank you.
For that great talk. Now, I don't know if the question is the audience there. Not yet. Questions? On. In the origin. The online participants, yeah, who have questions online. Any question? Can they hear me? Yeah, there is 1%. Another Raji. Okay, so you can go ahead, Dr. Olaniwaju Victor. Are you on mute and ask your question?
All right. Thank you. Can you hear me?
Yes, I can hear you very well.
I can hear you.
Very well. Okay. Okay. All right. Thank you. First and foremost, I want to thank Professor Bakare for this seminar, and I also want to appreciate the presenter for such presentation you have just given us for this period of time. I want to say thank you so much for all the models and all the series. So, but my particular question will go to the area of the machine learning. I'm so much interested in the aspect of the machine learning, and I want to ask a question that in the modeling of the mosquito structure that you have given, are we going to first of all do the mathematical modeling before applying the machine learning, or we're going to use the machine learning to directly provide the modeling structure? That's my question, number one question. Number two is that how do we get the data? Because when you're training a machine learning, you will need the data. So are we going to base our data on the stimulation from the PDE first, or we're going to base our data on the existing data on mosquito that you are describing? And if we are basing it on existing data, how do we get such data? That's my question. And lastly, is the only genetic algorithm that can be effectively used for as a machine learning tool for such approach that you have described? Thank you.
Okay, I'll come back to number 3 afterwards because I didn't think I quite caught that. But let me answer the first 2 questions first. Okay, so in terms of the machine learning approach, our approach is very much, it's a hybrid approach. Okay, so the fundamental component of our system is the dynamical model. Okay, so the idea there is we have a dynamical model that represents the linkages between climate and then the life cycles of the disease. Okay, because we know information about that from lab studies and so on. Yes, there are uncertainties. Okay, but we have concrete relationships there that we can represent in our models. Okay, and then the machine learning is like a layer on top that we then use for calibrating those relationships. In other words, to help us address the uncertainty that we have both in the lab studies themselves and in their transition from the lab into a, should we say, real world environment. Okay. Now we take that approach because, yes, in an ideal world, people can also apply machine learning directly and have a machine learning model. And we saw already, actually, for example, in the study I showed you from Maria in Greece, that's precisely what she did. She had Vectri as one model, but she actually had a multi-model ensemble. And one of those models was the random forest, which is a machine learning approach, which she trained on her data set of vector presence. Okay. But of course, the caveat there is that you need to have a large data set, which in Greece they did have, but it's often not the case that we don't have long and large data sets available in order to specifically train statistical approaches such as machine learning approaches. Okay, so that's why in terms of to have a flexible model that we can apply in different locations, we've definitely gone down the route of having a dynamical model component that we can then hopefully translate and apply in different areas. We can run the model in Nigeria, we can run it in Senegal, we can run it, as you can see, for vectors inside Europe. Okay, and then allow machine learning and on top of that to actually calibrate the model. Okay, so hopefully that answers the first question. So in terms of the second question, in terms of, because we've got machine learning for calibration, or machine learning in the case I was showing at the end. We're using machine learning to get the most optimal intervention strategies. It's not, again, it's not a data-driven machine learning. So that's to say, what we want to do is we have a physical parameterization in the model for SIT, okay? And what we do need to do is we need to confront that with data from field studies of SIT, where we have a field study in South Africa, for example, we want to process, where we have a control site and then we have a release site, and we know the climate there, and we can confront the two. And so they find in the release site, they have a certain reduction of mosquitoes. So we want to use that to help us calibrate our parameterization, okay, which has two calibratable, if that's the word, parameters, okay. So once we have confidence in our parameterization, we then apply the machine learning to actually basically derive the most cost-effective strategy, assuming that our parameterization is correct, okay, and that it does work, okay. And so it's a little bit like learning the machine learning how to play a game, if you see what I mean. So you know how, for example, they've shown with neural networks how you can basically just fundamentally give it the rules of chess, and then it can start playing itself. And over time, it learns to play chess just from like one winning, the other winning, and it can just learn how to play a game of chess. Or you can give the rules of the game of Snake, and very quickly a neural network can learn how to play the game of Snake and do extremely well to not bump into itself, okay? So it's a little bit like that, except that the game in this case is finding the best way of releasing sterile insects to maximize our knockdown. So you try with this calibration, it's like learning this game. It tries a strategy and it doesn't work very well. It tries another random strategy and that works a lot better. So those parameters from that better strategy are then passed on to the next generation, where you can imagine they're duplicated, there's some mutation. And this time, this strategy works even better. So over time, the model develops the best strategy, just like a neural network or a machine learning approach that learns how to play chess or learns how to play Snake. Here, we're just learning how to do interventions as if it were just like a game with a reward and a cost. So hopefully that kind of addresses the second need, where we're not using machine learning to directly just train on case data. The third question, I'm afraid I kind of missed that. I was wondering if you could repeat it for me, please.
I think the third question is, I think it's about the data you have actually answered. That do we have, okay, do we have other models apart from GA that can be used to train machine learning model? I think.
Okay, so you mean using models to train models? I don't know there. So here, basically, our approach here, I mean, again, to emphasize, is really to try and calibrate the model with lab studies, with in situ data, like we did, for example, for the egg data for the Aedes albopictus. No, we had egg data from 10 field sites. We used that to calibrate the model using this machine learning technique, but the calibration only allows you to, because you have this constraint from the lab studies, so you have a prior, you're only allowed to like move the model around a little bit in space. You can't just choose a wild set of parameters, because then you get penalized on the departure. So it's a little bit like having the ability just to move your model around a little bit in space to best fit the data, but without going to widely new, should we say, concept or completely unrealistic parameter settings. So that's the way the data is used inside the model in terms of the calibration. I don't know. I hope that hopefully that addresses that question.
Thank you very much.
Thank you, Dr. Olarewaju. Now, if anyone online that have a question, online participants, question. Okay, so while waiting for anybody here, we have Thank you very much. So my question is, I have a quick question here. The battery model that you talk about, is it possible to get the optimal timing of the occupation? Just to use the time
So-
of treatment.
Can I just ask, sorry, because the sound from the room is not very clear, it drops in and out. Would it be possible, is the microphone, would you be able to stand maybe nearer the laptop where the Zoom microphone is? Because I've got a feeling that the room sound is just picked up through the laptop microphone and it's not very clear to hear. If you stand nearer the laptop, I think that's used for the Zoom connection, I might be able to hear more clearly, sorry.
Okay, my question is, you mentioned battery model. So I want to ask, can it account for optimal timing of the infection so that to know when the time of deployment for treatment for malaria? So, and that's my first question. And the second question also, the machine learning model, is it built upon or which type of model? Is it an agent-based model, or which model was it built upon, or is it possible to be able to see the model or modify the model?
Okay, so the dynamical model runs with a daily time step. So it's a mathematical model. Each day gives you an output of like the vector density. It gives you an output of the status of the human population in terms of like the parasite rate. It gives you an estimate even of cases, although you have to take that with a little bit of a pinch of salt because, of course, the immunity model is very simple in the model. Okay, so the model integrates forward over a period of time. And so the idea is that it's able to represent the evolution and the delay between the rains and the actual malaria cases. So it is supposed to basically give you a daily evolution of the case data and so on. So the idea there is that, so of course in endemic regions, health services ministries are basically set up to, already have the timing of their insecticide residual spray and the IRS. They already know about, like, should we say, regular transmission zones, where the hotspots are within those regions of transmission. So the idea more at the beginning when we looked at the seasonal forecasting was to try and focus more on fringe areas where, for example, in West Africa, further migration of the monsoon or intense monsoon rains can change transmission, or in highland areas where elevated temperatures, for example, associated with El Nino years, can cause transmission to move to higher altitude in El Nino years and cause outbreaks. So the idea was for early warning in that regard. And so, yeah, so the answer is yes, essentially. It gives you a subseasonal evolution of both the vector densities and also the disease state. Okay. In terms of machine learning, the machine learning for calibration is a genetic algorithm. They sometimes refer to as a particle filter. So it's a very simple approach rather than like a full neural network. It's not necessarily optimal compared to a neural network approach. But one of the things I really like about it is when you're explaining, for example, to decision makers and so on, the approach is extremely simple and easy to understand. This concept, most people have an idea of how evolutionary biology works and how over time species can adapt to be more fit according to their environmental pressures that they have around them. And so because most people understand that concept, they also very clearly understand how the calibration works in this model. And I think that's actually a strong advantage, this simplicity of the approach, that there's no kind of big magical black box associated with, machine learning where the whole minimization process is not always clear to everybody. And it seems like a little bit of a, how do you say, magical waving the wand and an answer comes out. In this case, the technique that's employed, I think, is very straightforward to understand. And I think that's actually a big advantage, because then people know really what's going on under the bonnet of the tools that they're using. Okay. So yeah, the code is all open source. It's documented. I'm actually in the process of trying to translate the documents to a much nicer looking, read the documents. Let me see if I open a new tab here. Let me minimize this. And then if you just search for Vectri online. And so I'm in the process of trying to update this here. So under the documentation page, there is full details here of where to get the model, how to download it, how to install it, run it, change the vectors. This is not complete yet, though. Unfortunately, I've got a billion things on my plate at the moment. So the model description is still just placeholders. And the other bit, the machine learning part, is also not described yet under calibration. So this also needs to be completed. So I apologize that basically not all of these parts are here yet. Over the summer, I'm going to try and get up to date, but especially now with these new projects, I should have more person power to be able to spend a bit more time on finishing this up. But at least the material is there enough to be able to learn the model and actually run it and download it. It's just on GitHub, so you're very welcome to take a look, anybody in the room. And as I said, if you have, how do you say, if you have, an area where you might want to apply such a model, and you feel that the vector model could be a good model for this application, then I'd be very interested to hear from you.
Now, Stephen has a question. Okay, on the online. Stephen. Anybody having any question online? Okay, Stephen, can you go ahead?
He said he can't open his room again, so he sent his question for you.
Okay,
So, the question goes thus: how does Berkshire account for threshold when too much rain destroys breeding sites? Did you get the question, sir?
No, say again. How does Vectri account for? I didn't.
How does Berkshire account for thresholds where too much rain destroys breeding sites?
How does it? Sorry, it's not very clear. Account for Did you say thresholds or breeding sites?
Yes. How does Berkshire account for thresholds where too much rain destroys breeding sites?
Okay. Yes. No. So basically, the pond parameterization. Basically, if you remember, let me go back. I should share my screen again. Sorry, I preempted myself. So if let me just minimize the video. If we go right back, I don't know if you can still see my slides, to this equation page here. Okay. So in this larvae here, so when you have basically intense precipitation, it basically is folded into this mortality, and that's supposed to represent flushing and also breeding site destruction, okay, in a very simple way. So that means you actually have a nonlinear relationship between precipitation. Precipitation provides breeding sites, but can flush larvae, and also you could actually roll in this breeding site disruption. Now, of course, in cases where you have widespread flooding, of course, then this hydrological model breaks down. It can't account for all areas. So one of the things, when sometimes you have, for example, in Mozambique, where they had very widespread flooding after landfall of a tropical cyclone, and then you basically have complete inundation. That really, of course, that kind of situation can't be represented by this simplicity of hydrological model, where you get complete flooding that knocks down, and then you actually get a big outbreak once the flood waters start to recede, and you start to get just ponding and widespread breeding sites availability after the recession of the flood waters. Okay, so that kind of impact is a bit more tricky. One of the things I did want to do at some point was to try and even link to a hydrological model for, should we say, like temporary flooding of areas, things to do, like, for example, the river Niger. So rainfall in one area could actually affect breeding site availability downstream. We haven't managed to do that. There was a collaborator in Karlsruhe Institute of Technology. She tried to actually link the model to the surface water output from Wharf Hydro, so running high resolution model simulations. But in fact, the model didn't do very well, the Wharf Hydro, at actually predicting ponds. What tended to happen was when you had rain, you would have ponds that form for one time step, and then they would immediately disappear the time step afterwards. And so there was no sustained water availability. So we found that the model with my very simple pond parameterization here that I developed together with Ernest Asare from Ghana actually did a much better job of actually having the memory of ponds, which we saw, in fact, in, for example, these kind of simulations, where the model was really able to kind of get the evolution of basically water availability at these different sites, okay, on the subseasonal timescale. So yes, it does include flushing and that effect. But again, if you have data for that kind of effect and you want to confront the model with it, one could actually run the model and just focus on the hydrological component and compare it to your data, because that could help us. The hydrology is actually one of the most uncertain parts of the model, actually. And so anybody that wants to get involved and help us even prove further this hydrological linkage, I would be extremely happy to see that, because of the fact that the hydrology is the biggest uncertainty, in my view, between climate and the disease transmission.
Yeah, thank you, Prof. My question is basically on the model you showed earlier. So, and first of all, in the model you just showed, I saw that the lava development rate is made to be temperature dependent, but some authors made this to be both temperature dependent and rainfall dependent, in that they factored in the severe probability of different stages of the mosquito. Some of these authors lumped up the immature mosquito stage as just one compartment. So I want to understand your whole rationale behind making the lava development rate just to be temperature dependent, knowing fully well that sometimes the rainfall can impact the solar probability of the immature mosquito. So that is one. Then the second one is I also saw that in one of the models, you make use of maybe diffusional movement. I'm not so clear about what that means. And I want to ask for that if one want to factor in the diffusional movements and the work is data driven, how can one get data to capture that aspect? So those are my two questions. And then the third one is, I also saw that when you were trying to give us a diagrammatic description of the stages of the mosquito, I saw different stages of the lava, like lava 1, lava 2, and something like that before they move to the pupa. So I want to understand, because some of the things I've seen is just they move from the head to the lava to the pupa, then to the adult stage. But I could see different stages of the lava in some of the things you presented. So I want to have a better idea of what all of those means. Thank you.
Okay. Okay, a lot of questions. So let me see if I remember. Thank you very much for that. So basically, let's go back to this diagram here again. Hopefully that's still clear. So you're right to point out that the larvae development rate is a function of temperature. Okay, so that is basically this term here. So essentially, the larvae boxes here are not necessarily, and we might actually change that actually. So at the moment, it's not like L1, L2, L3 instars, okay? It's just basically the fractional development. So sometimes in fact, the model usually by default actually splits this up into 20 boxes. And the idea is just simply to be able to resolve very accurately the development of the larvae over time, okay, in order to get the delay between the rains and the vector explosion, should we say, correct, and resolve it quite well. Okay, we could have just used the same approach as we did for the gonotrophic cycle and just have one box or one box for each of the larvae stages, which we're actually thinking about doing actually to make the model faster. So we just have basically instar rates. The other advantage of just having instar boxes is it makes the comparison to field data much easier, because then of course we can directly compare, for example, survival rates directly to each instar. So that actually might change in the near future and actually make this slightly lower resolve, but we need to make sure that we have the numerics right of the model, that we don't mess up the delay. Okay, so the temperature basically impacts how fast mosquitoes progress from the egg right through to emergence. Okay, when it's warmer, they move through this array of boxes quicker. When it's colder, they go through much more slowly. And of course, the temperature impacts their mortality rates. The second question was, I don't remember. Sorry, I should have written it down as you were talking. Can you just remind me what the second question was super quickly? Hello? Do you still have the microphone?
Yeah. So, yeah. Yeah. So the second question has to do with diffusional movement. So I'm talking about
Yes, that's right.
if
Okay,
the D.
diffusion.
Yeah.
Yeah,
So
the D.
so
Okay.
if the work is data driven and maybe restricted to a particular state, so how does one get the value for this D or the data for this diffusional movement?
Yeah, no, that's a good question. So basically, what we did for that diffusional movement is we assumed a flight distance in the order of 500 meters. Most mosquitoes don't like to really go. I mean, Anopheles gambia, they can go up to a kilometer or more, but usually they stay within a few hundred meters. If they have a breeding site right nearby and a house full of people, they can go and get a blood source. They don't go very far. Okay. And so if you assume a kind of a random walk with a flight length daily of around 500 meters, it gives you a ballpark figure of what that kind of diffusivity should be. And of course, it depends on your grid scale. So that basically just means that if you have vectors in location, they can slowly move out into other surrounding areas. But it's really like a trickle. But I mean, again, as I tried to emphasize in the talk, that representation of just a diffusional movement is very simplistic. And it also, if you want to model things like the spread of tiger mosquito in Europe. So when we look at things like this presence, absence, okay. So the mosquito, as it spreads through Europe, actually, yes, it slowly diffuses out. So if you have an introduction into Trieste, slowly it will like spread around surrounding areas, okay. But by far the more efficient way of it basically being transported is where you get mosquitoes essentially getting trapped in cars or trains, and they just go with us in public transport. So they get moved and so basically we've seen there are studies that show how the movement seems to be along kind of like the road network and along basically rail network connections and so on. So we basically take mosquitoes. There might be a small population, 2 or 3 in a car, boom, take it somewhere else. So they fly out the car, and then they start a new nascent population that then basically diffuses out. So we don't have any of those non-local impacts in the model, which one might want to represent in a kind of stochastic way. I am very interested actually in trying to apply the model to invasive species. There's a lot of interest in Europe actually for this kind of application. And in order to do that, we will need to actually implement that. But so that was a long way of saying basically at the moment, the data parameter settings for things like the diffusion are just taken from a very idealized should we say, mathematical approach. There's not much data that can help us with that. You have also kind of like release recaptures and so on, but again, the uncertainties are huge in that kind of data. So, and it's important actually. One of the things I skipped over is when you look at the sterile insect technique, one of the parameters in our model, when I said about parameterizing to match observations, one of the key parameters is if you release 10,000 mosquitoes in a site, how they diffuse out, what area do they cover? So 3 days later, are they covering what kind of area are they covering, or are they pretty much staying locally? because that actually has a big impact of changing the mosquito density of these males and also the area that's actually impacted by that. So you can get very different results from the model, changing that parameter of how the aerial coverage, if you assume they just stay within a 500-meter radius, or if they spread out to a 3 or 5 kilometer radius, then you have a much lower density of sterile males over a much wider area. So these kind of things, people are studying. They're studying with like high impact photos in the lab. I was visiting a lab actually last week in Perugia where they were looking at mosquito behavior using high definition cameras and marked mosquitoes in a very large room in order to try and understand some of these things better about mosquito movements.
Right, thank you.
Is somebody speaking now? I don't hear. I don't hear. We perhaps need to move nearer to the laptop.
Yeah, so it's Emmanuel. Oh, what? Okay, so you said there was no data for the diffusion parameter used in the model, so that the value was assumed, right?
Yeah,
The
we
value
just
for
kind of did. We did a back of the envelope calculation just from just assuming that it was kind of a random walk with a kind of
Okay,
segment length
yeah,
of 3 to 500 meters. Okay, so that kind of gives you if you from mathematically speaking, if you assume a random walk and you have a kind of like a segment, so you say one segment per day, average segment length 500 meters, that gives you a diffusion rate. But of course, it might be overestimating the diffusion because, as I said, if a vector has got a house full of people and some breeding sites right nearby, they very well might just stay right where they are. They're not like curious human travelers that want to go all over the place investigating new horizons and so on. So it could well be that's kind of a flippant way of saying that my approach is maybe oversimplified.
okay, thank you.
Okay.
All right, then 20.
All right, thank you, Professor Tompkins, for the beautiful presentation. My question is on the SIT aspect of the talk.
Okay.
You mentioned SIT males and then SIT females. So I want to get some clarifications. Do female mosquitoes, are they also sterilized just like the male mosquitoes, or they obtain their sterilization via mating? I really like to get clarification on that aspect, sir. Thank you.
Okay, so the way that it works is basically in the labs, they have a whole bunch of mosquitoes. They sterilize them all, okay? But then they have these methods to basically separate the males from the females, okay? And so they separate the males from the females, and then it's only the males that are released, okay? So they have a whole population of mosquitoes, which are just basically sterilized, but they have to separate basically the males from the females, and that's because you can't release the females into the wild because they bite. But you could increase transmission of malaria because you'd be increasing a population of female basically biting mosquitoes. So no one would ever get permission, through the for the experiment to go ahead if that were the case. But they have methods. I was shown at IEA, I don't remember the details of how it works, but they have very efficient methods of separating the males from the females. And so it's only the sterile males that are released into the environment because they don't bite. And so the idea then is the model just records how many have been released. It has a simulation of the wild population already built in. And so you have basically a proportion of the, so when the female emerges and she needs to breed, excuse me, sorry, basically she has like a chance of breeding according to the proportion of sterile males. Sorry, I've just got over a cold, so I've still got a slight cough. Excuse me. So The model does actually have a parameter. I forgot to put in the equation in the talk, actually, which allows you to actually have the sterile males be less competitive in the wild with breeding. So maybe they're not so agile at flying or so on, and therefore have a smaller chance of breeding compared to the wild counterparts. It's actually quite a delicate balance, the radiation treatment. If you basically treat them with too high a dosage, then of course they don't live for very long and it's very inefficient. But if you do the dosage too low, then some of the males still might have viability, and actually then you could end up increasing the population by actually releasing more of the males and increasing the chances of basically viable eggs. Hopefully that answers that question. One could also adapt this parameterization to account for transgenic mosquito control measures. But we haven't done that yet. But it's something that could be quite easily done with this model. Now we have this parameterization in, so one could have, for example, transgenic mosquitoes and other such control methods. What we don't have yet is IRS in the model. That just requires basically parameterizations for enhanced mortality according to the IRS. So it wouldn't be difficult to do, but again, it's just finding the time of actually being able to collect the data and confront it in the model. So if anyone's interested, if everyone's got good data for IRS with like control studies and so on, and I'd be really happy if you were willing to look at that and actually just put a parameterization into the mortality scheme to account for IRS.
All right, Prof. Thank you so much for the lecture. I have 3 questions to ask. Number one, while you are presenting, you've shown us different functions that are functions of temperature and rainfall. Rainfall. But some of them we didn't see the explicit function as it depends on rainfall and temperature. You were just giving the so I would appreciate it if we can take a look at how really this function depends on temperature and precipitation. That's number one. Then number two, I also saw that on the SIT model, that's the sterile insect technique. There was a D there that is referred to as morbidity, and it came in as addition to both the female and the male compartments. I really want to understand why that is happening as an addition. So I want to understand that. And then thirdly, you presented a fitting process where there was you presented a fitting process where climatic factors were not included, and you showed that it was a poor fit, and the other one that had the climatic factors had a better outcome. Now, for those working on mechanistic models that are addressed to certain questions that may not necessarily be interested in looking at temperature and still wants to capture the data, the malaria cases data, for instance, for the sake of projection and prediction. Now, what's your advice? Is it that a model without the climatic condition may not be able to capture the race situation, even if the question is not looking at considering the effect of temperature or rainfall? Yeah, thanks.
Okay. So regarding the first question, on purpose, I didn't show the actual relationships of the model for 2 reasons. First of all, just because there's quite a lot of parameterizations in the model, and I didn't really want to have a talk that was full of equations one by one. Essentially, I probably would invite you to have a look at the description. The second reason for that, of course, is, in fact, am I still sharing my screen? No, let me just share my screen again. If I go, for example, to the model code, what we've tried to do actually in many circumstances is if there is uncertainty, if there are several papers which, for example, publish mortality schemes, okay, then what we're trying to do is actually give people the choice to implement different mortality schemes. And so what that means effectively is that you've actually got maybe 4 or 5 different parameterizations available in the model. It's not just a single one. And so, obviously in the context of my talk, it would be very difficult for me to go through these one by one. Okay, so if I show you now, I'm not sure you can let me make it a little bit larger, just to give you an idea here. This is the vector mortality. Well, inside this code, we have parameterizations for the Martin scheme 1, Martin scheme 2, the Bayer scheme, and then also the Mettelman scheme, which is applied to the Aedes albopictus. So you can see that some of these are the kind of relationships. So, Z temp is the temperature. So in this case here, the Martin's one is like basically there's a constant plus another constant times the temperature plus another constant times the temperature squared. So this is basically a quadratic relationship relating to temperature, okay? And then the Martin scheme 2 instead uses an exponential form. So again, you have basically constants here, the temperature and temperature squared, but inside a -1 over this factor exponential scheme. And then the Bayer scheme actually here is an order 5 equation. So here we've got this fit, which is temperature the 5th plus temperature the 4th plus temperature the 3rd. And so the reason why I didn't put these in the talks, of course, is, I mean, I could have put there more details, but it would have made it an extremely long talk. So I kind of invite you, everything is there. The nice thing about this model is it's completely open source. So you can see how these parameterizations have been built into the model. And then here at the bottom, we have the Mettelman scheme, which is for Aedes albopictus, you see. So hopefully that kind of like addresses that kind of issue. They're mostly this is the kind of level of complexity of this. They're kind of quadratic or exponential, quadratic, order 5. And in most cases, we've tried, not always successfully, to include always the reference as well. So when you look at, for example, the modules, if we go to the module for the constants, you can see that most of this routine is actually basically comments and not actually code. Constant as in Ehrman, Jepson 1947. We've tried to put in wherever we can the sources of this. Dupine 2004, stated in Bombley's, So you can see in each case where we've basically set these up and then we set the constants down below. We've basically tried as much as possible to document where we get these from. This is a very old paper, Detinova, but an absolute classic where we see where we've taken these values here. So it's completely open to dig into, and you'll see the sources nearly always where we can actually get this from. Look, again here, you see, this is a paper from Bonnet that was used for this. Okay, so hopefully we've written the model as much as possible with clarity and trying to state all the sources for these parameters and so on, and the parameterization schemes per se. But as I said, I didn't want to put them all in the model because then the model talk, the talk would have just been a set of equations, one after the other. The D, you talked about the D and the female and the male mosquitoes. Again, it's just to say that the mosquitoes, both the released and also the females, can diffuse over time. So you have a release site, but of course the mosquitoes don't stay completely locally where you release them. And so you will have this slow diffusion over time. And so we're trying to incorporate that into the simulation as well. Again, just using this simple diffusivity. And we've just assumed it to be the same for all species. So there's no difference between treated and untreated mosquitoes there, simply because the uncertainty, I think, is probably much greater than the difference between treated and untreated mosquitoes. Okay. And then your last question, well, I mean, some people have done very idealized models where they have no climate information taken into the model. So one example is the Swiss TPH malaria model, okay? So the Swiss TPH malaria model, which is called open malaria, they do produce simulations which have an aspect of seasonality. But they do that by, they're boundary condition is an EIR, so the entomological inoculation rate, the rate of infective bites per time. And what they do is they have that boundary condition defined basically as being a kind of like a sine wave to mimic the seasonality. But in their simulations, they have no differences in transmission from one year to another. They have no nuances of the actual nature of the subseasonal variability because they don't have any information about the climate at all. And that's what we do have in the model. If you notice, we managed to get the seasonality completely correct of albopictus because we had those explicit climate relations. So in fact, I think to get a good representation of subseasonal variability and to get a good representation of interannual variability, there's no getting around including accurate climate information into your model. And indeed, Swiss TPH now have a collaboration with us where we've tried a hybrid approach where they have Vectri trying a simulation of EIR, which is then used as a boundary condition for their model, which has their model has much more evolved parameterizations for interventions, which have been tested in numerous different field studies. And so they have a very good representation of interventions, but they want now to use our model to allow them to account for the climate in terms of subseasonal and interannual variability. I think there's no getting around that. So otherwise, you're just reducing yourself to having very simple toy models of climate using sine waves or so on as boundary conditions. So hopefully that answers the third question.
Okay, thank you so much. Two of the questions have been answered. Then I was also talking about the SIT model, where we have D representing mobility. So I said I want to get clarity on that also. Thank you.
You know, I think I answered that one when I said that the D for the mobility is treated the same as for normal mosquitoes. I did answer that. So the mosquito mobility is just assumed to be the same. There's no modification of the parameterization for, you know, lack of mobility of treated sterile mosquitoes. They're just assumed to have the same mobility. And it's an important parameterization. It's actually that diffusivity of the mosquitoes is actually important for that SIT. That's one of the parameters that one would need to basically calibrate, I think, when we actually confront it with campaign data.
Okay, thank you. There is no other question. Thank you very much for your time. Look at some further collaboration.
Okay, it was a pleasure to join you. I hope it was understandable. And as I said, if anyone's interested, go and take a look at my website, clone the model, play with it, criticize it, improve it. So it is there to use. It's a community model, and any feedback would be greatly received, both for strengths and weaknesses, whatever. So please help yourself. I see there's a hand raised. Victor, did you want to add something?
Yes. Can I go on?
I think so, yeah. I'm ready.
Okay, yeah. Sorry, I just want to ask that, do we have the slide for the presentation? And also, you mentioned your sites. I didn't get the URL.
Okay, so I haven't got the link for the site in the talk. So just if you do a Google for Vectri, you'll find it straight away. VECTRI, Vectri. So you'll come straight across my webpage. Yeah, and I'm happy to circulate the slides. The only thing I would ask everybody is just for the SIT work is not published yet. So please treat that with, how do you say, caution. Don't post it on a public website. Or maybe I'll just take those one or two slides out until I manage to how do you say, sort that paper out, which I want to do in the next month or so. But I'm happy also, I can email it directly to you, Victor, if you like. If you just send me an email, you'll find my email on the site, and I can reply to you with a copy of the talk as well,
so
and I'll pass it on
all
to
right,
Emmanuel.
is the email on the site? Is the email on the site?
Yeah. You'll find me there. So if you just look for Vector, you'll find me, and then you just navigate through my site. You'll find my email there. It's just my surname, Tompkins@ictp.it. But you'll find it on the site as well.
Okay, thank you very much.
No worries. Okay, great. Well, thank you everybody very much for your patience and your attention, and all your wonderful questions. That was an intense question session. It was really nice to see. So I'm happy there was interest in the model.
So I'll keep in touch. Thank you. Ciao.
Okay. Bye-bye, everybody.
Bye.
Bye-bye. Bye-bye.
Because and stuff.
Yes.
Sorry.
So what we're going to need to talk about
Yeah. So thanks for being part of that just completed exercise. So I would like to